Okay, so I'm going to try and start a series of videos where I kind of explain the content of Mochizuki's inequality. Okay, so I guess I'm just going to start by stating the inequality in full. So let me state it like this. So Mochizuki's inequality. Okay, I'm going to just give the statement here. And it's not going to mean much until I explain a lot. So there's going to be a lot of terminology. Okay, so for E, an elliptic curve, over a number field F, sitting inside initial theta data, and so initial theta data is a big tuple. It consists of an algebraic closure, an elliptic curve defined over F, and then there is this there's another curve that comes from here. So this is kind of like a level structure. This is a prime number. This is a lift of places on the field of moduli to another field. This is a non-empty collection of bad places over the field of moduli, and here is kind of a generator for one of the groups associated with this thing. So maybe this isn't the cleanest way to say this, and I'll talk about that in a second. Okay, so when we have this, so then one has the following. It says that the degree, so this is an Arakelov degree, so, and we'll say this is in the field of moduli of the elliptic curve of some Arakelov divisor, so we'll call this the Q-pilot divisor, is less than or equal to, and okay, so now we have some measure space. So there's kind of two ways to say this, right? So we can either say that this, so let's do it like this. So this is minus the Arakelov degree here, but it's kind of some like normalized Arakelov degree. It's not quite an Arakelov divisor. And what we'll do is we'll take P of Hull of U theta like this, and I have to describe what these things are. Okay, and it turns out that this Arakelov degree, this is also equal to, okay, so this is the statement here. Okay, all right, I have to describe all these objects, but it turns out that the left hand, the right hand side has a volume interpretation. Okay, and I'm just going to continue with this volume interpretation. So this is a lot of this is good. There's a lot of exchange between Arakelov divisors and adelic volumes. So let me just say what this is. So I'm gonna ... Let's go to the next page. So it says that minus this LGP degree. So this is for the same field of this P of Hull of U theta. Okay, this is going to be equal to log nu of L. So this is like a log measure. It's not quite a log measure, but it's like a log measure of Hull of U theta. So here, this L, this is like this is like an idyllic, we can call it a Mochizuki log measure space, and I will say a little bit more about what that means. Okay. All right. So let me just say that. Let me say a little bit about this now. Okay. So maybe we can start with the left-hand side, and then I'll start to break down the right-hand side. Okay. So okay. So this has to do with Q pilots or Q divisors. Okay, so maybe I'll just state the definition real quick. So this PQ, so this is going to be an element in the Arakelov divisors of Q join J of E. That's the J variant of the elliptic curve. This is the field of moduli, sometimes written F subscript mod. This PQ, it's defined to be equal to the sum. This is not going to be cool. So this is going to be the degree of so the degree, or let's say the order with respect to V. So this runs over V in V of QE, QJE. This is the field of moduli of now let me just write down what this is. So we're going to have Q V. So this is we'll take a place of so I'll remind you guys about the what happens, but for any place of bad reduction, so this is V an element of I should have done this V bad mod. This is a non-empty set of places of bad reduction. Okay. So with a residue characteristic not equal to 2. Okay, so it doesn't have to be all of them. So for example, you could just pick one of them, and then V here. Okay, so this is the thing here. Like, oh, and I have to double underline this. I need to tell you what this is. So here, let me just say this. So recall that for E an elliptic curve over L, this is this is L, a finite extension of QP with, let's say, J. So this is all on the back of the Silverman topics. So this thing is greater than 1. So this is with the L norm. So here we're going to use this this is a finite extension. So this is a non-Archimedean norm. This is with the normalized norm. If this is bigger than 1, then E L bar here is isomorphic to EQ L bar. So this is some Tate uniformization. So this is, all right, let's just call this a Tate curve. And where here EQ of L, there's a map from here to, let's call this phi, to L bar cross modulo Q here Q to the Z. So for some Q called the Tate parameter. Okay, so this condition here with the J invariant, the absolute value of the J invariant bigger than 1, that's going to say that it has bad reduction. So I just want you to recall that if you have bad reduction, say if you have okay, so what can happen with bad reduction, right? So if you have additive reduction, you can base change and it'll become good or multiplicative reduction, and here it's saying that you're not gonna have good reduction. There's not potentially good reduction, and when that happens, you'll have when you have multiplicative reduction, then after another extension, right? So here's over the algebraic closure. You'll have you'll have an isomorphism like so. So this is isomorphism. This isomorphism here is over L bar, the algebraic closure of L. Okay. All right. So this is what happens, and then there's a relationship between the valuations of the tape parameters. So there's kind of a fact. Okay. So fact. Did I say that this is the... So I didn't say what this thing is. It's Q V1 over 2L. So L is a fixed prime number. All right. So okay. So one of the facts that I'll prove is in a second is that the valuation K of Q, or let's do this like this, or L of Q. So this is equal to the valuation of the minimal discriminant or delta of valuation of delta of EQ. And then that we have this, and then also, so for such EQs are actually minimal models, at least local minimal models, minimal Weierstrass models. So that tells you that this thing will actually be a factor of the minimal discriminant. Okay, I'll go back to that in a second. So we've kind of described this one side here. I just wanted to remind you that the degree, so a reminder, maybe I'll repeat this again, so that this Arakelov degree of these guys here, so let's say for V naught dividing infinity, so this is the inertia degree times ln of the residue characteristic. All right. Okay. So all right. So that describes one side here. The other side. Okay. Let's describe the description of the theta pilot object. So, or the theta pilot region. So description of the theta pilot region. Region, and this is kind of going to be the multi-radial version. And these are all words. I know that are kind of weird, but I'll describe what this means. So there's okay. So let me just say this. So where do I start? So we're going to start with so for p theta. So what is an LGP divisor? Okay, so here we can start with some p, right? And it'll be a tuple of divisors, pj, for j is equal to 1 up to L minus 1 divided by 2. So here, pj this is just going to be a divisor here. Div hat in div hat of Q J. Well, okay, we'll do it with this one. I guess we could define it with any field, but we'll start here. And then you define this degree hat LGP of such a P. This thing will be equal to. This is going to be equal to the average of all the degrees of the other ones. So this is going to be 2 divided by L minus 1 times the sum from J is equal to 1 up to L minus 1 divided by 2 of the following of deg hat Q J E PJ. So this is just the average. The average of a tuple of divisors, of a tuple of degrees of a tuple of Arakelov divisors. Okay, so all right, that's one thing. Now so there's going to be an exchange between these things, so that there's a procedure. And I could have done the procedure on the Q side as well, for taking P and associating it to some omega P, which is going to be, so this is going to be, okay, so here, let's do it like this. So this guy is an element of some measure space, so a measurable set. This thing here is one of these, we can call this div hat LGP, so Q J of E. All right, so I mean this again. This holds generally without these fields, right? Without these specific fields, such that here so this negative of the degree of this LGP degree of P is equal to this log volume L of omega of P. Okay, so there's a conversion between these guys and these guys, and I'll write that down later. All right, so let's go back. So what are we doing? We're defining both of these objects on either side. Okay, I'm just said that there's a procedure for switching between one and the other. Okay, and so now what is the multiradial region? So let's say theta pilot region. Okay, so first we're going to define p theta. So this is going to be a tuple so this is going to be a tuple of p theta j's from j is equal to 1 to L minus 1 divided by 2, where p theta j is just going to be like the Q pilot, and we're going to do ord v, and then we're going to Q double underline, so that's the 2Lth root of this thing. And then we're going to do that to the j squared, and then we're just going to put in that v there. So this is for v, an element of v bad mod. Okay, so these are these guys, and we have this Q pilot divisor. Okay, so now what we'll do is we define, so then we can associate this region omega p theta. This is in this Mochizuki adelic measure space L, which I haven't really described yet. So this is for the place V. Okay, and then what we're going to define here is so there's this U theta, which is this is the multi-radial version, and it's kind of a blurred version of this thing. Of the theta pilot region. Okay, so and so this is equal to what we'll do is we take, there's going to be a group action, int1, 2 here. So this is a group spanned by two subgroups. Okay, this is going to act on omega p theta. Okay, and this thing here is going to be acted on by a certain indeterminacy. Ind3. Okay, and then I have to kind of describe actually what this thing means. But what's going to happen is that this requires a bit of explanation. Okay, we'll develop a notion of indeterminacy diagram to deal with this. Roughly, not roughly, but Ind3. It's a map from the power set of this region to the power set of this region. Or power set of this fake adelic measure space to the fake adelic measure space. Okay, so we're not quite done yet. So we need to define the hull. Okay, so the hull here. Okay, so this is this takes regions to new regions, new larger regions. And essentially what it's going to do is it takes all possible morphisms in some diagram that you can get, and then it'll take the union of all the images under all possible morphisms from one thing to another. This has to deal with these so-called log links. Okay, so that's what Ind3 is, and then okay, and so I needed to, the last thing to do was to define the hull. Okay, so for hulls, okay, so it turns out that let me just say, so it turns out that L here, okay, at least in kind of in a naive sense, there's an anabelian interpretation of a certain structure associated to this, that this thing is a product over P of LP, okay, and LP, where LP is a direct sum of fields, including an infinite place. Is just a product of fields. A product of p-adic fields. So for okay, so to define a hull of omega, this will be contained in L. For omega contained in L, so it is enough to define it locally. Okay, and so what I mean is that so so what we can do is we'll be able to break this up. So we'll be able to, we'll actually just be working strictly with things that are products in here, and what we'll do is we'll the whole of so if omega is a product of omega p, then in other words, if omega is a product of omega p, then whole of omega is defined to be equal to whole, let's say, the product over p of whole of omega p. Okay, so now let me say what the whole of omega p is. Okay, so the local definition. So if L is let's write it like are we gonna use direct sums? Let's use direct sums. K1 direct sum, K2 direct sum K. I don't like that because I'm gonna use that for K's for tensor products later. Okay, so L is K1. Oh, sorry, shit, I did it again. So if L is L1 direct sum L2 direct sum dot 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 direct sum, let's say LR, and omega is a sub. So and omega is a subset of L. So all of these are going to be p-adic fields. Subset of L. Then the whole of omega is going to be the intersection of so let's say over the set of D. Let's do DL1 R1 direct sum DLR. Oh shit. Let's do S. S. RS. So polydiscs. Such that DL1 R1 direct sum blah 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 direct sum DLS RS, so that this thing contains omega. So this is then the whole. Okay, so if we have a direct sum of p-adic fields and a region inside this direct sum, the direct product, whatever, then the whole of L, right? No, sorry, whole of omega is this thing, defined to be this thing. So this is just the, so this is the definition. So this is just the smallest polydisk containing omega. Okay, okay, so all these things are the idea is that sometimes the idea is that so like our so regions like let's say factors of U theta don't have module structures naturally. And this whole construction is just taking the smallest module, is taking the smallest module, this you know the And I haven't really said what the module is, what the ring is, but let's say it could be over, say, the intersection of all those fields. O of the intersection of all those fields. Smallest module containing the region. And this is, let's say for, so what module, what's the, how do I change the color? So for what module, so this would be like the, so this would be like an OL module, OL0 module, where L0 is the intersection, is L1 intersect L2, intersect LS. Okay, so all right, this is one thing, and then this is used. There's actually going to be, well, there's actually kind of like two. Well, okay, I'll have to describe what this is going to be used for, but there's actually going to be like two holes. So what we're going to do is we're going to take some region that's interpreted within absolute Galois groups of p-adic fields. It's kind of glued together. And then and from this, you'll be able to go to two other different interpretations. And using this hole construction. This hole construction then allows you, theoretically allows you to compare so like this region U theta to another region PQ, or another region associated to the divisor PQ. Okay. So, all right, so I've said a little bit about this. I guess I didn't really define what, so I didn't define what in3 is. Okay, so now we have some group action here. So what we've done is we've taken our, okay, so let's just kind of recap. So this is a region associated to this thing. The log volume of this, the Mochizuki log volume of this, will be equal to the like LGP, or this precession degree of this Arakelov divisor thing. Really, we're going to be encoding these in categories later, but this is kind of the structure right now. Okay, then there's this U theta, which is the kind of messed up version of this omega theta. And we'll have a group action here, and then we'll have this thing where we enlarge this region by taking all these different maps, which will be described in a bit. Okay. So, okay, so then we described the hole. The hole is just the product of other holes. And now I guess it remains to just say what L is. Okay, and to say what L is, so what is this measure space? L is L. Okay, so there's a couple various versions of this. So Mochizuki writes these as, so if you want to look this up, notation. So there's kind of four flavors of this thing. This is like I think he puts the Q here, or just put the Q, and then he'll have some sort of a prime strip, F, VQ. I think. There, and then he'll put a label, he'll put a label here for another copy of this thing. So these are like so these are the measure spaces that we'll deal with. So then you can replace this little doodad here. So this thing is going to be interpreted within this structure, and then there's four layers of this thing. So there's one built from, like, essentially fundamental groups and monoids. There's one built from fundamental groups. There's one built from, so fundamental groups of hyperbolic curves, like a series of them. There's one built from absolute Galois groups of fields. That's kind of like the lowest one. And then there's one built from absolute Galois groups of fields with monoids. And then there's compatibilities between these. Right, and so this is the largest one there, and I'm not sure if I'm forgetting a symbol, but yeah, and so this indicates that it's going to be over all the places. Okay, and so for this to work, right, so what do we fix? So we fix So to get this to work, let me say not to get this to work, but to define this, right? To define L, we need to fix the following. We need to fix K, an extension of L, or an extension of the field, okay, of a certain field here. And then we need to fix F naught. So this is going to be in here. So a subfield. Okay, and so in our case, F naught is going to be, this field of moduli. And then we need to fix here a section. So here's all the places of K. It maps to all the places of F. And then what we can do is we can take all the places, we can take this thing, and so we define V underline to be S of V of F naught. So these are lifts of places on this kind of bottom field to K. All right. So we have this thing, and so the image of this thing is this V underline. Okay. So we need to fix all these things, and now I will go ahead and define this. So L. So there's kind of I guess 3 kind of layers of this. So L. Okay, it's going to be equal to, well, the product over P. LP. LP. In turn, so this is going to be the direct sum from J is equal to 1 to L minus 1 divided by 2. So L is this fixed auxiliary prime number of the following A. So they're fake adels. Okay, let's do this. V underline F not P. Okay, so these are tensor products of fake adels here. And so here, A V underline F not P, tensor J plus 1. Okay, so this thing is going to be equal to so what I'll do is I'll take the direct sum of V here. Okay, so let me introduce a little bit of notation too. So some notation. So if V is a place of F naught, then we define V underline will be S of V. Okay, so this is just the lift of V to this thing here. And so like we're taking a place down at the bottom level to the top level. All right, this particular instances of K, F naught, and V will be in the initial theta data. Okay, and so now I'm going to take this, and I'm going to take, this will be K, V underline. All right, and we'll do this to the tensor J plus 1. All right, and okay, so this is these are the spaces here. By the Chinese remainder theorem, so this is a. I'll say a little bit more about this, but by the Chinese remainder theorem, this is just a direct sum of fields, direct sum of p-adic fields. And then we'll give an explicit description for this. All right. All right. So now I want to say a little bit about the measures here. So what about these measure spaces here? So so these are the spaces. Okay, and then I'll break that down a little bit in a second. So this thing for a region B that's contained in here, it's going to have a measure. So a Mochizuki measure, right? And it's going to be defined to be the following. So it's going to be the sum over all the primes of just the log measure of the local places. And then so this is going to be the projection onto P of B. So we just take some B that's contained in here, we project it on each factor, and we take all the measures. Okay, so now the definition of this measure is reduced to the definition here. Okay, so so log of L P. So now I'm going to suppose that B is in this region now. Okay, at log nu of this thing of B. So what I'm going to do is I'm going to do nus for like probability things and mus for some other type of normalized measure. Okay, and so this is going to be the expectation of okay, so now what we're going to do is we're going to, I'm going to need some space. Okay, so we're going to take the let me leave some more room here. Oh, well. Okay, so this thing is going to be the expectation of, okay, now I'm going to take the measures over these little pieces. That's how this works. Okay, so we do A, V underline, like this, J plus 1. And then I project onto P and J. So there's a P component and a J component of B. Okay, and then this is going to be averaged over, okay, I'll put the line here. So this line is supposed to go kind of there. For 1 less than J less than or equal to L minus 1 divided by 2. Okay, so that's that goes with this guy over here. Okay, and then finally, so maybe I can make some more space over here. Right, so I'm going to define, so this one goes over here, this one goes with here, and this one goes with here. Okay, so I'm going to define, then I'll explain what this expectation is. So log nu, okay, and so this one's going to require a bit more notation of A, V underline here, J plus 1 of some region. So this is going to be equal to the expectation of, okay, so now I'm going to do log mu of L. All right, now I'm going to have to define what this thing is here of, so I project onto a certain factor. What I'm going to essentially do is I'm going to write this out as a bunch of tensor products, and then this is going to correspond to the direct sum of fields coming from the factorization here. Okay, so this is this region here, like so, and then we're going to do V here. Okay, so now I have a vector in here, P to the J plus 1, like so. Okay, and so what we're going to do is we're going to take this tuple of things, and we can lift it to an underline version using this thing here. So this also works for tuples, right? That's what this thing is. So let me just say a couple other things. Okay, so let me explain what these LVs are. So here, so we'll have this. So let me just write it out. A tensor J plus 1 of so these are kind of fake adeles. I like to call them fake adeles. So this is equal to a, we wrote it down like this. P of k v underline here, tensor to the j plus 1. Okay, and then we can break this down as follows, right? So we'll just do, so this is a tensor over QP. Okay, we'll do this. All right. Tensor, this is over QP. V1 divides P. So these are those lifted places, like so. And then tensor, so these are direct sums. These ones are tensors. Tensor, they're all over QP. Okay, and now we have a direct sum of K, V, J. So Vj divides P. So this is implicitly over bad places in V underline. But I didn't really specify what V underline was, but in practice it'll be these V underlines, and this turns out to be a direct sum. And now we'll do V0 Vj. This is the fiber over P to the j plus 1. So this means that you're looking at all of these V underlines that go over P. And it's not really all the V underlines, but let's say that it's all the V underlines for now. E. Okay, sorry. Of K V0 tensor V underline J. And so this thing here, this is what we defined to be equal to L of V like this. So this is a direct sum of fields. This is a direct sum of fields. And V underline like this. So this is an element of V underline P to the j plus 1. Okay, so here in particular, this thing looks like V0 Vj. Okay, so it's one of these tuples. Okay, and so this will decompose as a direct sum of fields. The last thing I didn't say was how these expectations work. So the expectations. All right. So for any finite probability space, E, let's say S, and then we'll say a collection of WS. So for S and S, so these weights will so here the WS are weights with so they're just numbers in between 0 and 1 that add to 1. Okay, so we define for any finite probability space and a function f from S to let's say it could be a vector space, or it could be, let's say, the real numbers for now. So we define the expected value of f of S for x and S. So this will just be the weighted sum of S and S of WS f of S. Okay, so this is just the usual thing. Okay, so this is the usual expectation here. All right. So okay, so finally, I guess we have to define these log measures here. Okay, so let me just give a definition. So if So what about these normalized measures? Okay, so let me just say a little bit. Well, okay. So how about I'll leave this at this, and then I'll stop the video here, and then I'll have a video, one video where we'll talk about these Mochizuki measures, and then in another video we'll talk about the exact hypotheses on initial theta data for this thing to run. So oh, okay, wait. Before, let me actually, I want to kind of give you. I want to. Let's actually not do that. So I want to be able to have this maybe self-contained, so it's completely correct. So okay, so let me just give one more definition. Definition. Okay, so if V is a finite dimensional, QP vector space. So define so log mu v bar to be the normalized let's say the normalized Mochizuki log measure. Okay, so I guess I should define the notion of a Mochizuki log measure. The normalized measure. Okay, I'm just gonna say the words, and then I'll define what a Mochizuki log measure is. Maybe this isn't the best terminology, but whatever. Okay, so so what we'll do is we'll take log mu v here of a region to be equal to log mu v of omega. So this is the Haar measure on this QP vector space. So this is as a topological vector space divided by the dimension of V as a QP vector space. Okay, so this is what this thing means. So for a big vector space V. In particular, this definition appears here. So this will be QP vector space. The dimension of this is just the the product of the dimensions, or the sum of the dimensions in the. So it depends if we're using the direct sum version or the direct product or the direct sum decomposition. But it'll be anyway. It's a QP vector space, and this is how you compute. This is what it is. Okay, so and I guess I can say what a Mochizuki measure is. Okay, so all right, since we're talking about this, let's talk about the definition. So a Mochizuki log measure. Okay, so we're kind of doing a convention where if something isn't exactly as you'd expect it to be, well, it's we'll add the word Mochizuki. Okay, so so a Mochizuki log measure on a direct sum of p-adic vector spaces so let's call it V. It's going to be a direct sum of I is equal to 1 up to m of vi, right? Is a weighted sum of normalized log measures. Okay, so this is the normalized log measure here. So I'll do it like this. Log nu, okay, of A. So this will be a region, so this will be, okay, so A, let's say, where A is going to be the direct sum of AI. So maybe these is just a region. It doesn't really need to be a group or anything. So I is equal to 1 up to m of the sum here, I is equal to 1 up to m of wi of log vi here, log mu of vi of ai. Okay, so it's a weighted sum of normalized log measures, and we'll say that and the sum of the wi's for I is equal to 1 up to m is equal to 1. Okay, so this is a Mochizuki log measure. Okay, and cool. Okay, so one more thing. So definition. Okay, so let k0 over qp be finite. And so let, and then we're going to do this tuple, v log nu like this, be a Mochizuki normal, so a Mochizuki log measure okay, we say this thing is, so this is a nu here, it's a v, is Mochizuki normalized. I mean, this is actually, this is maybe how you'd expect it to go. If, so if for all x and k0, we have the following condition. Log nu of xa, okay, and this is for every measurable set, is going to be equal to log of the p-adic norm plus log nu of a. If in all, let's say a measurable. Okay, and measurable will just mean hard measurable or product of hard measurable sets. Okay, so okay, so normalized log measures are Mochizuki normalized, but not all Mochizuki log measures are Mochizuki normalized. Did I say that right? Okay, well, hopefully I did. Okay, so okay. Also, okay, neither normalized log measures or these you know, or Mochizuki log measures. None of these are logs of measures. Okay, and these are what would appear. Okay, so so I think that's where I'm gonna cut this video. All right, thank you for watching. I'm gonna do the theta data video now.